Hey, this is G-Lab. Welcome to a quick introduction to plate tectonics. I'm Mr. G. I'll be your lovely host. Hey, this is just a very quick introduction to plate tectonics and how it all came to be and the theory itself. It all really started with this guy, Alfred Wegener, a German, who a little over 100 years ago proposed, hey, if you cut out the continents, they seem like they fit together like a jigsaw puzzle. Kind of nice. Maybe they were once together and have since drifted apart. And so he came up with this idea called continental drift, where at one point in history, perhaps all of the continents were one big landmass, and they have slowly drifted apart from each other. So he went looking for evidence for this. He really only had a hypothesis, just an idea, really, and so he went looking for evidence to support it. And some of the things that he found was that the rock formations match up across the oceans. So, for instance, rocks and even mountain ranges stretch across an ocean, and he thought, well, you know what, perhaps there wasn't always an ocean there. Perhaps these were once together. So South America and Africa, perhaps they were right next to each other, and then since that time they've been split apart in some way, that they've been drifting away from each other, separating these mountain ranges. He found the same thing with some fossils that he looked at. So here's a fossil of a land reptile that lived back in the Triassic period a long time ago. And it was about 3 meters long, so it was a big sucker. And he found that it only lived in South America in a certain range and in Africa in a certain range, and that it kind of made sense that perhaps that range was all one at some point, and it really only split apart sometime after this reptile became a species. And so the fossil remains seem to match up pretty well. And the same thing with here's a freshwater reptile. Obviously, freshwater reptiles can't swim across an ocean because it's salt water, and land reptiles can't just kind of swim over there, or pretty unlikely that they would hop on a log or a raft and land somewhere else that would be a suitable climate and habitat for them to live in. So as he started to piece together various fossils from plants or from other animals like this guy here, he found that, yeah, if all of these continents were all one big place at one time, that probably makes more sense. So he presented this idea to some of his colleagues, and of course they thought he was crazy. They said, yeah, continents aren't moving. We don't see them moving, feel them moving, and what would move them? That was the big flaw in Wegener's theory, is that he had no explanation of how this happened, what caused the continents to move. He kept looking, he kept compiling evidence, he kept trying to figure out a way that what would push these continents, but he was never able to really satisfy the scientific community. And so when he died a couple decades later, the idea essentially was kind of swept under the rug until about the 1960s. The 50s and 60s saw a lot of development of maps of the seafloor. So we used sonar and mapped the seafloor and started to find some interesting features down there. So for instance, one of them is a ridge system that runs right down the middle of the Atlantic, like a seam, and right between those continents that seem to fit together pretty well. And as we looked in detail at what that looked like, it was a ridge with little fracture lines on both sides, and started to realize that, oh, maybe there's something to Wegener's theory. Other evidence started to pile up. For instance, the location of earthquakes, the pattern they seemed to have was along these very linear features. There's a few random ones here and there, a few outliers, but essentially earthquakes started earthquakes were happening right at the boundaries, right at the edges of these tectonic plates, and so that was some further evidence. And there are, of course, several other lines of evidence that are also quite compelling, and these are just the basics. But it led us to this idea of perhaps the Earth's crust, the lithosphere, is fractured into a number of what we now call tectonic plates. And there are about 20 of these plates, roughly. Some are very large, like the Pacific plate or the African plate or the Eurasian plate. And other ones are quite a bit smaller. And so if you look at the map of the world, you can see that there's, maybe a dozen or so on this map, and there's a few smaller ones even in these. But essentially, the Earth is broken up into large plates. Some of these plates have, so for instance, like the South American plate has not only a continent on it, but it also has oceanic crust making up part of that plate as well. And other plates, for instance, like the Nazca plate or the Pacific plate, are pretty much completely oceanic crust. The idea, of course, that these plates then move around, and when they crash into each other and slide past each other, different features are formed. One little plate that's very important to us here in Oregon, of course, is the Juan de Fuca plate. And this little guy here, as it crashes into the North American plate, is responsible, of course, for our Cascade Mountains and for the reason that we have the climate that we do where we live. So looking at this from the side, you can see that there's various different ways that plates can move. Some move apart from each other, like here, these two continental plates moving apart, forming a rift valley. These two plates here are moving toward each other, creating a subduction zone, subducting underneath, and as that plate goes underneath, it melts and comes up to make a volcanic range of mountains. Also, there's a trench right off the shore there. And then other places where oceanic plates are spreading apart, we'd call that another divergent boundary that we call an oceanic spreading ridge, or a divergent zone here. It's creating new crust. And finally over here are two oceanic plates colliding together and again melting, and we have volcanoes forming. This one here represents a hot spot, which we're not going to talk about in this video, but this would be similar to Hawaii, just an individual spot here and there. So what we now know is that there, of course, are various layers of the Earth, and underneath the Earth we have these enormous convection currents happening in the mantle. And as that happens, what it's doing is it's dragging the plates along with them, as if the plate was a rubber raft floating on a river. So it's a river of lava, and it's a rock raft. So as these continents, these giant rock rafts, float around on top of the mantle, that is what's causing plate tectonics, essentially, is that they're crashing together, and here's a spot where the convection currents are going down. So obviously you have a convergent boundary here, where the convection currents are going up and spreading apart. There you have what's called a spreading boundary, or a divergent boundary where they're spreading apart and creating new crust. So we're going to take a look real quick at the three main types of plate boundaries, real basic, but a quick overview of these. So divergent is where their plates are moving apart from each other, they're diverging. Convergent is where they're converging, they're coming together. And transform boundaries are where they're sliding past each other. The word trans means along or across, so like the Transcontinental Highway, for instance, or Transcontinental Railroad is across the continent. So transform means across or sliding past each other. So let's start with divergent. These are boundaries where two plates are moving apart from each other. In this case here we have two continental plates that are moving away from each other, and they're forming a valley between a small rift valley, it's called. As they continue to spread apart, you end up with a slightly wider and wider rift valley, and you can see this one's filled with seawater now, pretty narrow, and this is similar to what's happening in the Red Sea over between Africa and the Middle East. And as that continues, of course, they just spread farther and farther and farther apart. And so this is how, for instance, the Atlantic Ocean is formed. You've got a mid-ocean ridge here. There's a ridge because the magma is sort of pushing up here, and also this basalt here is less dense, and as it gets older and older, it gets denser and sinks lower. But essentially, you've got a mid-ocean ridge with this fracture, this rift valley right down the middle of it, where lava is coming up and becoming new crust. And so you can see that mid-ocean, that mid-Atlantic ridge right down the middle of the Atlantic, and that's where two plates are pulling apart. Other places where that's happening, well, you can see that happening right here off on one part of the Pacific Ocean. You can see that these two plates, the Nazca plate and the Pacific plate, are pulling apart from each other, and eventually this Pacific plate moves this direction and eventually slams into the Eurasian plate and gets subducted down underneath it. You can also see divergent zones over here in the South Indian Ocean as it comes up to here, and look at that, it goes right through the Red Sea. And so the Red Sea is actually splitting apart and becoming, it's going to become wider and wider and perhaps eventually become an ocean. The same thing's happening here in the Eastern Rift Valley of Africa, the African Rift Valley, where Africa is actually being ripped in half, torn asunder by tectonic forces, and eventually this will either become two separate continents or at least have a sea between them. Now, it doesn't happen very fast. This comic here about Rex, hurry. You don't really need to hurry. The continents really don't move very fast, only a few centimeters a year at the most. So it's about the same speed that your fingernails grow. So if you watch your fingernails grow, that's about how fast the continents are moving. But if you give that, say, 100 years, it can move, maybe a meter or so, or a few meters. And if you give it, say, a few 100 million years, you can actually have these divergent boundaries widen enough to eventually become wide enough to be an ocean, like it has happened in the Atlantic.
In an underwater eruption, the molten lava comes in direct contact with the cold seawater.
So here we have what's happening at the bottom of the ocean in these divergent zones. Magma comes up, cools into crust,
and forms characteristic pillow-like shapes.
And this is actually called pillow basalt because it kind of has this pillowy look to it. And this is a constructive process, not destructive, but constructive because it's constructing, it's making new crust. And so at those divergent zones, you're constructing new crust and making more basalt that will eventually spread apart and apart and apart. Someday, perhaps shoved back down in when it gets to a subduction zone. All right, speaking of coming back together, the second type of boundary is a convergent boundary, and that's where plates are coming together. And the first one we'll look at is two continents coming together. Here's India and the Eurasian plate. And so India used to be its own little continent, its own little landmass, and over the last 70 million years or so, it has moved north and slammed into Asia. So if we think of this as India and this as Asia, as these two things come together, there's a lot of mess that happens in between. Essentially, things just get crumpled up. And so you've got sedimentary rocks that were just off the coast, for instance, of each of these that were scraped up and folded, and you'll find fossils from sea creatures high up in the mountains, sometimes as high as 20,000 or more feet up in the mountains. That used to be on the bottom of the ocean. They've been scraped up in this collision. A lot of metamorphic rocks associated with these kind of boundaries because there's a lot of pressure as these two continents come together, and they create a lot of heat and pressure to make metamorphic rocks. Here's a nice view of it from space, and what you see is India basically crashed into Asia, and kind of like when two cars crash together, their hoods just get crumpled up, and that's the same thing that happened here, and those crumples make the mighty Himalaya mountains, tallest mountain range currently on Earth. Another kind of convergent boundary is when you have a continental chunk of crust coming together with an oceanic chunk of crust. So a continental plate and an oceanic plate coming together, and what happens is the oceanic plate is more dense, and so it ends up subducting underneath the continental plate. And as it does so, it does scrape some things off usually, and also it forms a deep trench. In fact, the deepest places in the ocean are these deep ocean trenches that are, some of them, like the Marianas Trench, is over 30,000 feet deep. You can actually fit Mount Everest all the way into this trench, and it would still be underwater. So deep, deep trenches. And as those plates, as that lithosphere gets subducted underneath the continental plate, of course, what happens then, we see some melting occurring, and some of that comes out as volcanoes. You can see other places here where it hasn't quite reached the surface, and it's formed maybe granite intrusions that would cool underground. But you've got this volcanic arc of mountains here, just inland. And then finally, the transform faults, or transform boundaries between two plates. You have two plates sliding past each other, one going one direction, one going the other. And you can see by this the creek here that sometimes what happens with the creeks, and this even happens with roads, in fact, is that creeks and roads will actually, over time, have to adjust to the new landscape, and so they start to sort of get offset like this. And roads do the same thing. Over the course of decades, you'll see roads that are actually as many as several feet apart, so they have to repave them and smooth them out. Here's an example of that. You can see this bending of this looks like an old creek bed, I think here. Um, but this is the San Andreas Fault, a classic example of a transform fault, and it runs right through um, all the way north through California, right through San Francisco. They're famous for some really large earthquakes here because of that, because of the fault as it moves past each other. It grinds and slips and occasionally slips a large amount and shakes the earth. And what you'll see here is that this little chunk of California down here is on one plate, and the majority of California is over here on the North American plate. What you'll find is that Los Angeles, if you give it enough time, will eventually move up next to San Francisco as San Francisco moves down toward Los Angeles. So they're going to be neighbors. And of course, it's many millions of years in the future, but eventually Los Angeles and San Francisco neighbors. So three main types of plate boundaries: divergent, convergent, and transform. All right, that was just a quick introduction to plate tectonics. Much more detail and much more evidence, of course, has been found since the 60s, and this will just give you the quick overview. Thanks for watching.